taking a bit to get the computer set up. I chatted a file. I'm going to send it again for the people who arrived since I sent it. And then we can get down to business. Sorry for the delays. Okay, so yeah, what I mean by special angles is something like you should know how to do sine of pi over 3. Whoa. Can't even write it. Sine of pi over 3, that would be 60 degrees. So, I mean, either you just have that memorized, or when I do this, I draw a little picture of 60 degrees, and I remember that the sides on such a triangle go like that. That's a root 3 over there. And so the sine would be the opposite over that hypotenuse, which is root 3 over 2. Right? So you should know how to do that either by just because you memorized everything, or by some other, I don't care how you do it, but you should know what those values are. And then I say, in parentheses, I said be able to find the corresponding special values of inverse sine and inverse cosine. That means, once you know this, that means that inverse sine of root 3 over 2 equals pi over 3, right? So this is what I mean by you should be able to find the inverse trig functions of special values. So root 3 over 2 is a special value of the inverse sine. All right. Okay, continuing on the list here. You should know derivative and antiderivative of sine and cosine. I hope you do. You don't have to know the tangent or all the other weird ones. Just sine and cosine, I will expect you to know. All right, and then here's a list of formulas I will give you. I plan on writing exactly those formulas at the top of the test, whether you're going to need them or not. So if you see them on there, it doesn't mean you have to use them, but these are the formulas that I promised to give you. So I'm going to give you those formulas. And I say in parentheses, you should know the corresponding integrals for the inverse trig functions. What I mean is, I'm going to tell you, for instance, the derivative of inverse tangent is 1 over 1 plus x squared. That automatically means that the integral of 1 over 1 plus x squared is inverse 10, right? Plus c. I'm not going to tell you that integral, though, because I am going to tell you the derivative, so you get the integral for free, but I'm not going to write it down. All right? And then here I put the answer. So I got kind of ambitious this morning before I came to class, like after I got to campus, but before I came to class, I thought, I'm going to go through and write down, figure out all the answers, and I didn't have enough time. I ran out of time. I only got through number 12. So I will give you the rest of the answers later on. I got ambitious. I should have come to class sooner and set up the computers. All right. So anyway, this is the review sheet. Like I said, these maybe I didn't say. You know what I want to do today is just talk about whatever things you want to do. I think if there are ones that you're looking at on the sheet and you say and you feel like maybe it would be good if we tried an example like that, I would be happy to do them. I thought probably it would be good if we did an example of the volumes of revolution, whether you guys asked me to or not. So I did prepare such a problem right here. It says rotate around the y-axis the region bounded by y equal x cubed, y equal minus 1, x equal 1, x equal 2. Actually, before we do this particular question, I meant to ask, are there any general questions about the test? So I said it's going to take up the full class period. What else can I say about it? It's going to be like similar in format to the quiz questions or the homework questions. No multiple choice or anything like that. Just straightforward. I ask the question, you write the answer. You will not be using calculators, so if you have any like numerical answers, I will not expect you to simplify them. Actually, on the first question there on the sheet, you will see sort of the format of the answer I would expect you to give me. You don't have to try and multiply or add things together or whatever like that. Any general questions about the test? I would I would appreciate it if you come to class and take the test in person. I don't know. We have some people I know who are just decided they're going to stay home the whole semester, and that's fine. If you haven't otherwise, told me about it, I will expect you to be in person. That's a little better setup for giving tests, in my opinion. I know some of you already have talked to me about it, so that's fine. All right. Any other general questions? All right, let's get down to let's do this volume of revolution, and then we can talk about other things too. You folks back home doing all right?
Yeah, we're good, Professor.
All right. I didn't mean for that to do that. Okay, I'm gonna pin that action. All right. Okay, let's do it. So, it would be a good idea, first of all, when beginning any one of these problems, is to start off by drawing the picture as best as you can. Now, this is y equals x cubed. I hope you know what that looks like. So, my curve is y equals x cubed, which looks like this, right? And then we have bounded by y equals x cubed, y equals minus 1. So that's down here. X equal 1, so that's here, and x equal 2, which would be here. So this is x equal 1, this is x equal 2. So the region I'm talking about is this, right? It's the region in between those four curves. I hope everyone's clear on how I got that picture. And then we're going to rotate, I said rotate around the y-axis, so it spins around that way. All right. Now, I didn't say which way to do it, shells or washers. Yeah, question?
I was just going to say, are we doing this with shells we took on some bowl shape, which is easier to do with shells?
Yeah, this one, I would say the shells is a better strategy for this one because, well, one thing is the shell formula naturally works the best when it's being rotated around the y-axis. So this is a good, I mean, a general idea. You should consider doing the shells if it's rotated around the y-axis. And the idea behind the shells is to cut out sort of a little rectangle like this and rotate that little rectangle around the y-axis, right? This is the whole point of the shells method. The washers for this one would be harder and kind of impossible because the washers would look like, here's my shape, right? And it spins around this way. Now, if you want to cut it in such a way that you get washer-type shapes, you have to cut this way. But, and actually, for the cuts that I drew up there towards the top, that would not be a problem. But then down here, the inner radius and the outer radius are different. Like here, the inner radius uses the curve, and the outer radius is a constant. But then at some point around here, it shifts, and now both of them are constants. This makes the integral very hard to set up if you're doing it using the washers method. So for this one, don't do the washers. Do the shells. All right, let's do the shells. So you got to remember the shells formula. I get leftover stuff down here. So we're going to do the shells. The shells formula is integral 2 pi x f of x dx. How about the integration boundaries here? Anybody got an idea? What do you think?
Say from 1 to 2.
Yeah, from 1 to 2, right? You want sort of from here to here on the picture. This is the range of x values that you use on the shells. You only take the x values from one side of the figure. It's going to be 1 to 2 in this example. Okay, and then we have, so, I mean, you can factor the 2 pi out like we usually do. 1 to 2 x times f of x. Now, this is the height of the shells. So what I want to use for f of x is this distance right here, all right? Sometimes this is just equal to whatever curvy function they told you, but sometimes it's not quite equal to the curvy function. And in this example, it's not quite equal to the curve x cubed. So this f of x, you should not just plug in x cubed there. Anybody got an idea? What should it be? Yeah. X cubed plus 1 is correct. Yeah, x cubed is the distance from the curve to the x-axis. But in this picture, we also have this much extra height to the shell, which is 1 extra. All right. So in my my f of x in this case is x cubed plus 1. X cubed is the height from the x-axis to the curve, but the shell height is actually 1 more than that height up to the curve. So right here I go x cubed plus 1. All right. And this is the setup. That was the hard part. You know, from now on, it's just a fairly straightforward integral. How would we handle this integral?
Just do it as it is, leave that 2 pi on the outside, and then, or you have to distribute it.
Yeah, let's distribute the x on the inside. That's the only sort of trick, such as it is. I don't like this. I see a little chatty chat, but I don't think. Well, that was when I sent the file. Yes, we got to distribute in here. That's the only really interesting thing to happen. So it's going to be x to the 4 plus x. And then I do the integral. So we get 2 pi. The rest is easy, although, you know, you got to do it. 1/5 x to the 5 plus 1/2 x squared. Plug in 1 and 2. And let's just do it. 2 pi, and then I get 1/5 times 2 to the 5th plus 1/2 times 2 to the 2 minus 2 pi. 1/5 times 1 to the 5th plus 1/2 times 1 to the 5th. And that's it. This, I would expect you to leave the answer like that. I'm sure you could simplify parts of that, but I don't care about that. All right. In some cases, and you'll see this if you look carefully at the problems in the sheet there. Sometimes if you end up with logs and trig functions in the answer, I might say something like simplify all the logs or simplify all the trig functions if I want to force you to actually plug the values in at the end. All right, any thoughts about that one? Great, that was a shell one. We might as well do a washer one. Let's do, so like I said, this particular shape does not work well with the washers because the format of the inner versus outer radius actually changes as you go through the shape, and that's not ideal. But we can do sort of a simple variation. What if I'm going to sort of defile this picture? What if I just take that much of it? So I'm going to do x cubed. So let's do y equal x cubed. X equal 1, x equal 2 like before, and also y equals 1. This will cut the picture off so that it's only this part of it, all right? That part. And how about we rotate that around the, well, we could do it both ways actually. Let's rotate it around the x-axis, see what we get. And then if you're not satisfied yet, we could also rotate around the y-axis and see what we get. Those will give you two different answers, of course. So let's rotate around the x-axis, first of all. That way, so it's going to be sort of another little thing over here. This is like a Christmas tree stand or something. All right. And I think we should do the washers with this way, and we're going to slice it up sort of like that, right? You slice it in the vertical direction, so my integral is going to be in terms of x, going across from left to right. And I use the washer formula, so it's going to be, would you agree, it's from x equals 1 to 2, and then it's going to be pi times the outer minus the inner, right? I think in this case the inner radius is a little easier, although I guess neither of them is all that complicated. Can anyone say what's the inner radius in this case? It would be 1, yeah. On this picture, the two sort of the inner radius is this one, and then the outer radius is this one up to where the curve is, right? Yeah, the inner radius is always 1 as you move across this figure. It is. Look at the picture. So the inner radius is 1. It's 1 squared, but that's not going to matter. How about the outer radius? What do you think? It would be measured from the curve point all the way down to the x-axis. I think it is just x cubed. You have to sometimes, you have to wonder, do I need to, can I just use the formula exactly as is, or do I need to modify it? In this case, you can just use it as is because I want the outer radius would be the distance all the way from the point all the way down to the x-axis. That is just x cubed. You might wonder, what about the fact that there's a gap here? Well, that's why we have the inner radius as part of the formula, is to deal with that gap. So the outer radius is just x cubed, and that has to be squared. All right, and that's how we do it. So this is the setup. Again, in my opinion, the setup is the hard part. From here, we just do the integral as usual. So we need to figure out what is x cubed squared. Remember the rule for that? Yeah, you multiply the exponents. So it's x to the 6 minus 1 dx. And then we do the integral. So pi 1/7 x to the 7 minus x. Plugging in 1 and 2. So it's pi times, 1/7 times 2 to the 7 minus 2 minus pi times 1/7 times 1 to the 7 minus 1. And that'll do it. Any questions about that one? Again, I would not expect you to simplify the answer any more than that, although I'm sure you could if you wanted to. I'm not into 1/7. I don't know about you. Or 2 to the 7. Sure, you can do that. Yeah. Yeah, you're certainly, so at this point, instead of the way I wrote it, you could write pi over 7 x to the 7 minus pi times x. Yeah, that's fine. And then do the same plugging in. Yep, you'll end up with an equivalent thing. All right. Do you want to try that rotating around the y-axis? Let's try that. Rotate the same shape around the y-axis doing washers. And then I think we can move on to something else, unless you really love these guys. So again, the shape is here, but this time I'm going to rotate it around the y-axis this way. And you could do this one with the shells or with the washers, but let's do it with the washers this time. So my sort of slicing, in order to get the washer shapes, you're going to have to slice it up this way, which means my integral will be dy, not dx, which means you have to rewrite things in terms of, y's in terms of x's, rather than x in terms of y, rather than y in terms of x. So my original formula was y equals x cubed. I'm going to have to rewrite this as a function of y. What would that look like? Yeah, x equals the cube root of y. You just solve that thing again, but for x instead of y. All right. And that is now the formula for this this curve here, which is on the inner surface of this volume. All right. Okay, so I'm going to do my washer formula. It is integral pi r outer squared minus the r inner squared. This time dy, not dx. And you can see on the picture what we just said, that formula, cube root of y, that is the inner radius of this volume. So it's going to be integral pi. The inner radius is cube root of y, and that should be squared because of the squaring in the formula already. How about the outer radius? Someone want to shout it out other than my two regular customers? What's the outer radius here? The inner and the outer, on this picture would be, here's the inner, and then Here's the outer going over there. Someone back home can shout it out, or someone in the flesh.
Is it x to the third?
X to the third is the inner radius. I want the outer. What do you say? It is 2. Yeah, the outer radius on this picture is the distance all the way out to the end here. And that's 2, according to the setup. This picture is not as well labeled as before, but it's the same picture as before. This goes out to 2. All right? So, 2 here, with the squared, of course. And the inner radius is cube root of y. All right? Only ingredient missing here is the integration boundaries, which I didn't fill in. Remember, I am integrating with respect to y here. So you should be writing down the y values at the bottom and at the top of this figure. The one at the bottom, I just said, you cut it off at y equals 1. So down here should be 1. What's the upper one there? The y value at the top. This I actually didn't tell you. You have to kind of figure it out. It's 8, yeah. How'd you get that?
So you just have to plug to your original equation.
Yeah, right. Because this curve here, as a y in terms of, or as a, yeah, y in terms of x is y equals x cubed. And so when x is 2 on the right side, the y value there will be 8. So that's a little figuring you got to do from 1 to 8. All right. That's that. This was a harder setup than the other one. And I'm noticing it's already 9:30, so maybe I'll just leave it at that. Can I just say, etc.? You can finish this integral. Yeah, how do we handle cube root of y squared? Any suggestion? Yeah, you make that 2/3 y. So this is integral 1 to 8. Let's put the pi outside. And then it's 4 minus y to the 2/3. Oh, we might as well just do it. Can't resist. So the antiderivative now will be 4y minus, it becomes, you add 1 in the exponent, 2/3 plus 1 is 5/3. That's the hardest part. Like this. I think it's 5/3. And then, so this is pi times 4 times 8 minus 3/5 times 8 to the 5/3. And then subtract pi times 4 times 1 minus 3/5 times 1 to the 5/3. And I leave it at that. You actually can simplify 8 to the 5/3, but not today. Not today, Satan. I'm off the bottom. So, all right. So that was volumes. I hope that wasn't. We didn't spend too much time. The volumes will be on the test, but it's not going to be like half of the test. So don't spend all your time studying about those. What else do you want to talk about? If you see other ones on the paper, I'm going to try and leave these for you to do on the paper, but I can invent ones that are similar if any of them look. Okay, find the inverse of something or other. Yeah, those we didn't do a lot of them mostly because they're fairly straightforward and it's maybe something you did in high school. Find the inverse so that one there. How about I will invent something like find the inverse of maybe y equals how about that? I don't know how this is going to work out, but let's find the inverse of this function. I should have written with a f of x because it's supposed to be a function. I mean, it doesn't really matter, but so remember the way you do this is you write it as y equals whatever, and then you solve for x instead of y. That's the idea. So I'm going to write y equals 5 over x plus 4 squared, and then I'm going to solve it for x. Or if you prefer, some people learn to swap the x for the y immediately at the beginning and then solve for y again. If you want to do it that way, that's fine. I prefer to do it this way. It doesn't matter. How would I solve for x in this case? Any suggestions? Yeah, I want to get x by itself on one side. I think the first step towards that end would be multiply this denominator over to the other side. So I'm multiplying both sides by x plus 4 squared, and it ends up saying x plus 4 squared, y equals 5, right? I want x by itself, so maybe we can divide by y to put y on the other side. It'll say 5 over y. We getting anywhere? What next? Yeah, I want to sort of kill the squaring, which is happening on the left side, so let's take the square root on both sides. When I take the square root on both sides, the square goes away on the left, and on the right I end up with this. And then we can subtract 4, and we'll have it. So x is that guy minus 4. And so the inverse function, f inverse of x, is this formula down here, only I use x where y is. So it's going to be square root 5 over x minus 4. That's the inverse function. So, I mean, this doesn't really require any fancy tactics. It's just sort of high school algebra, moving stuff around to solve for x. Yeah, I mean, so at this point you could write this function is f inverse, like in this format I wrote it in terms of y. F inverse of y is 5 over y minus 4. But at that point it doesn't matter. You can call this variable whatever you want, so you might as well call it x again. Although on the test I'm not going to be too picky about how exactly you write the answer. If I really want you to write it in a specific format, I'll tell you what I want to see. Sure. Derivatives of logs and exponentials. So something like number 10 on the paper? Or 13? Yeah. Is that what you're talking about? Yeah. Okay, so how about let's do derivative of x to the 5 plus 5 to the x minus natural log of five x squared. How about that? Take the derivative of all of that, yeah. I'm trying to mess with your head by putting x to the 5 right next to 5 to the x. They look kind of similar, but they're actually totally different, the way that you have to handle each of these. How do you handle x to the power 5? Yeah, this is not a trick question. That's 5x to the 4, which does not require any fancy business. That's just what you learn, when you first learn how to do the derivative. How about 5 to the power x? This is completely different. You may be tempted to say x times 5 to the x minus 1, but that's not right. When the x is in the exponent, you use a different rule.
It's going to be 5 to the x times ln 5.
Yeah, 5 to the x ln 5. This is actually one of the rules that I said I was going to give you on the test. The first one in the list of formulas I will give you. All right, so, I mean, you have to know that there is a formula for that. I hope that you know. And then minus natural log of 5x squared. How do you handle the derivative of the natural log is, well, so the basic formula is the derivative of ln x is 1 over x, right? So whatever's inside the log goes in a denominator. And then you have to do the chain rule. You multiply additionally by the derivative of whatever was inside. So this is going to be 1 over 5x squared times the derivative of what's on the inside is 10x. And that's it. So that's the derivative of that. whole thing. Any thoughts or questions about that one? That one was not so taxing. How about this? What about derivative of the log base 2 of 8x over cosine x? How do you like that? Yeah, this is log base 2 of 8x over cosine x. So, first of all, you have to think about how do I handle the derivative of the log base 2? This also is in the list of formulas I'm going to give you. It says derivative log base b of x is 1 over x ln b. All right, so we're going to use that formula sort of at the first level. And then, as always, we have to do the chain rule. You additionally multiply by the derivative of what's on the inside. But how about this? How do we plug directly into this formula? You just write this stuff, where instead of x, you use all of that thing, 8x over cosine x. So what it looks like is 1 over 8x over cosine x times ln of 2. This is what you get when you plug directly into that formula. Instead of x, I'm using 8x over cosine x, and instead of b, I have 2. And then I must multiply by the derivative of the inside. And what do I do for that? The derivative of 8x over cosine x? Yeah, you got to do the quotient rule for that. Did I say maybe I should have listed that in the formulas to memorize? I will expect you to know how to do the product rule and the quotient rule. Hopefully you already do. So the quotient rule here is going to be the bottom times the derivative of the top, which is 8, minus the top, which is 8x, times the derivative of the bottom, which will be minus sine x, divided by the bottom squared, like that. And you should not attempt to simplify this, although I'm sure you could if you had to, but I would say leave it at that. That's a bit of a harder one. Any questions about that one? What else? We got about 10 more minutes.
Quotient rule is f of g prime minus g of f prime over g squared, right?
If f is the top and g is the bottom,
Okay.
it's g times f prime minus f times g prime over, right, over g squared.
Low D high minus high D low.
Yeah, if this is the top, this is how I remember it. Ho D high minus high D ho over ho ho. Yep. I'm not ashamed. What else? Take a look here. Do you remember how to do these logarithms by hand?
Yeah, the 2 e's of the answer equals what the source was. Does that make sense?
Yeah, although you don't always use e. So, like for instance, what is log base 4 of 64? NHS is nursing. So, for an extra challenge, you can try to get there without going outside. It is possible. There's a bridge on the second floor. So if you go up from here to the second floor, you can walk across. And remember how to do this? Log base 4 of 64. The idea is you should translate this into some kind of exponent. So this formula here is equivalent to 4 to what power equals 64. And you just have to kind of remember how you go from one side to the other in this you know, the one on the left is like the logarithmic version. The one on the right is the exponential version. But once you're at the exponential version, you should just be able to guess what exponent is appropriate. And what exponent do we want there? 3. Yeah, I think 4 to the third power is 64. Maybe you don't know your fourth powers, but you know, on the test, if you saw this, I would expect you to just do something like, well, 4 to the 1 is 4, 4 to the 2 is 16, 4 to the 3 is 16 times another 4, which is 64, and then you realize you got it. So the question mark is supposed to be 3. So that means log base 4 of 64 is 3, right? That's the kind of thing you have to think through in order to figure that log out. Any others? Folks back home, you got any ones you want to talk about? We got 5 more minutes. He doesn't. He's saying no.
Can we do logarithmic differentiation?
Sure. Logarithmic differentiation. So that would look like usually this is used when you're trying to find the derivative of some kind of monster quotient with products in it. So let's try x to the 4 times x squared plus 1 to the 5 over how about 8x to the 10 times 3x plus 1 to the 15. Can you believe it? 15. All right. You could, in theory, do this using the product rule and the quotient rule, but you would never want to do that. You'd have to do a quotient rule with products inside and chain rules inside of those. So instead, do the logarithmic differentiation. The way you do that is you write y equals this whole thing, and then you take the derivative, then you take the log on both sides and simplify as much as you can, which is typically quite a lot in a product and a quotient. All right, I'm going to put ln's on both sides. Would you mind if I just squeeze them in there? And then we are going to simplify the log on the right. So on the right side, first of all, it's a big quotient, which means I can subtract the numerator from the denominator. So this is the same as log of x to the 4, x squared plus 1 to the 5, minus log of 8x to the 10, 3x plus 1 to the 15. All right. Can we break this up anymore? I think we can. These are now products inside of the log, so you can break those up as pluses. So this is going to be log x to the 4 plus log of x squared plus 1 to the 5. And then I have minus, and this one also can break up log 8. In fact, here I have a product of 3 things, don't we? 8 is the first thing, and then x to the 10, and then that other thing. So I can split it as log 8 plus log x to the 10 plus log of 3x plus 1 to the 15. All right, can we simplify any more? I think we can. What else can you do with these logs? Move the exponents into the front as coefficients. So this becomes 4 ln x plus 5 ln x squared plus 1 minus ln 8. You can't do anything with that. And then as I go, I'm going to distribute that minus sign. So next comes minus 10 ln x, and then minus 15 ln 3x plus 1. All right, these, and this is as simple as this is going to get on the right-hand side. This equals ln y. This is a big one. All right, what do we do next? We take the derivative on both sides. So on the left side, I get 1 over y dy dx. And on the right side, we take the derivative of all those logs. And each time we get something like 1 over x, right? So 4 log x just gives you straight up 4 times 1 over x. You don't have to do any chain rule or anything like that. Next, we get 5 times 1 over x squared plus 1 times 2x. That's the chain rule. That's where that 2x comes from, the derivative of the inside. So it's about time to go, so I'm going to do this a little quickly. What about ln of 8? That is going to be 0, right? Because that's a constant. And when you take the derivative of a constant, you get 0. And then, so this is, I'll just put 0 so you know what happened to it. Minus 10 times 1 over x. Minus 15 times 1 over 3x plus 1 times 3. That last times 3 there is because of the chain rule again. And we're almost done. The final step is to multiply y over to the right side and write it in terms of x again. So I'm going to multiply this over here and then write the original formula for y in terms of x. So we end up with dy dx equals all of this stuff. I'm going to condense a little bit. 4 over x plus 10x over x squared plus 1. I'm combining some of the coefficients. Minus 10 over x minus 15 times 3, 45 over 3x plus 1. And then times y goes right here, which is my original thing off screen at this point. X to the 4, x squared plus 1 to the 5 over 8x to the 10, 3x plus 1 to the 15. So this is my answer. Come on now. All right, sorry to squeeze that in at the last moment. Okay, so you should expect from me either later today or sometime tomorrow the rest of the answers, but I hope that you can get started on these if you like. If you can't manage to get the answers, feel free to, ask questions by email. I would be happy to, if you want to, send me a photo of what you got. If it's not working out, I can tell you where you went wrong or something like that. All right, see you all on Friday. Bye-bye.
Thank you.
Yeah.